for the law of refraction. We know speed equals distance over time. Hero said that light will take the shortest path, so distance. Fermat actually said that when we talk about refraction, we can't talk about minimizing distance, but in fact, we are going to talk about minimizing time. So he's approaching this in a slightly different way. So he said that the rays of light that travel between the two medium do not try to minimize the path, but they try to minimize the time. Now, how does that work? So let's write this down and I'll show you how this works. So law of refraction okay, this is my incident ray. But this time it's not being reflected back, it's actually getting transmitted. So if I have a point A here, and if there was no medium in the middle, will this light do that? All the way to point B. There's no medium in the middle. But what if I put a medium in here? And I call this one N1, and I'm going to call this one N2. Then he said that the correct path that light follows, so this is Fermat, when there is a transparent interface between the medium, light will not travel from A to B. Technically, this would be the shortest path, right? In terms of distance, yeah, from point A to point B. But if you have a transmitting surface in the middle, light will not follow this path. He said, actually, the ray of light actually travels the path of least time. That's another form of variational principle. So this is the generalized principle that he came up with, and Hero's principle becomes a part of this generalization. Okay, so what do we know? We know speed equals distance over time. If I call this distance A, I can call this distance X, and I can call this distance C. That means this distance is C minus X. And let me call that B. Take a second to note what all of these distances are. That means that is also B. And that is my incident ray. And that is my incident angle, theta I. May I rewrite this formula as T equals distance over V? Then in medium 1, may I call the time it takes in medium 1 to go the distance A0, where this is 0, divided by the speed in medium 1? And can I call this in medium 2 the time, I'll call it T1, the time it takes to go, let's suppose that this can't go to B, right? So this certainly cannot be true, but it has to do something else. So say like, let's say that this goes kind of close, but not that close. It goes here. This is my C minus X, and this is my transmitted angle. Theta T, I'll call it T for now. So can I say, if I call this distance, I don't know, C, can I call this a OC divided by V2? So the time in one medium and the time in the other medium will be different. It will. Oh, you're right. I should call this. Come up with another one. D. You want to call it D? I'm going to call this point D. So then this will become D. Does everybody understand how the times change between one and the other? Because we know the speed is going to change between one and the other medium, right? We know that. Okay, so now the total time it takes to go from point A to now point B, can I write that total time to go from point A to point B? What will that be? T will be T1 plus T2, which means I can write this as AO divided by V1 plus OD divided by V2. Okay, now coming back to this picture right here. Where's my right angle triangle? That's my right angle triangle. So what is this side actually? Good. And what is this side then? Correct? May I plug these values in this equation that I have? So may I write this as a squared plus x squared square root divided by V1? And may I write this as b squared plus c minus x squared square root over V2? So I'm going to plug these in here. I'm going to write T equals square root of a squared plus x squared divided by V1 plus b squared c minus x squared square root over V2. And what did he say? We have to minimize time. So how do we minimize this time? Speed equals distance over time, correct? Mm-hmm. What are the three variables we have? T, x, and v. How will we minimize time? We have to take the differential of time with respect to x. Because we are minimizing time, we have to do dt over dx. Okay, so we have to now minimize time. To minimize time, we have to do dt over dx and put it equal to 0. So this will be 1/2 a squared plus x squared, 1/2 minus 1. And then 2x. And then 1 over V1 will remain there. And this would be 1/2 b squared plus c minus x squared, 1/2 minus 1. then c minus x, 2, and then minus 1. And then 1 over v2. And we have to put all of this equal to 0. And then the 2's will go away. This 2 will go away. And then a half minus a 1 is minus a half. So I'm going to write this in one step. So this is now going to be x over v1 square root of a squared plus x squared minus c minus x over v2 square root of b squared plus c minus x squared. Okay, now here comes the fun part. So this looks really complicated, right? But stare at this picture that we had. We need x over ax. So what does this become? X over a squared plus x squared. If this angle is theta I, what is that angle? There we go. That's also theta I, right? So can I write sine of theta I as x over a squared plus x squared? Similarly, if this is theta transmission, can I write sine of theta t is the same as c over x divided by b squared plus c minus x squared square root? So then may I rewrite this really complicated, weird looking thing and this really complicated, weird looking thing as 0 equals sine of theta I over vi 1 minus sine of theta transmitted divided by v2. Is it starting to look pretty? May I rewrite this as sine of theta I over v1 equals sine of theta transmitted divided by v2? Is v equal c over n? So will this become sine of theta I divided by c n1 equal sine of theta t divided by c n2? C's at the bottoms go away. And what are we left with? n1 sine theta I equal n2 sine theta t. Woohoo! Isn't that beautiful?